Hello everybody, this video is going to be about the mole ratio and stoichiometry. So stoichiometry is a big funny sounding word that really just means that we're going to be calculating the amount of reactants or products that are involved in a reaction. So you're going to have questions like, how much do I have? Or how much do I need? Or how much could I make? Things like that, where you're going to be using different compounds in the same problem. It's very similar to molar conversions like we've been doing, but the big difference here is that we're going to convert from one substance to a different substance. In order to do stoichiometry, we need a balanced equation. The coefficients inside the balanced equation are going to tell us the ratios of what we need. They're basically like our recipe. We're going to know that for every one of these, we need 4 of those. Things like that. Without a properly balanced equation, you won't be able to do the stoichiometry questions correctly. So, we have been probably, most of us, thinking about these reactions as how many molecules are needed. For example, to perform this reaction, we need 2 molecules of hydrogen gas, 1 molecule of oxygen gas, and it will make 2 water molecules. But if you remember, it's not very convenient to do things in individual molecules. They're so small, we can't really measure that on our scale. So we're going to be using big batches of them instead. So instead of thinking about these as individual molecules, let's think of them as moles of molecules. So I'm going to need 2 moles of hydrogen molecules. I'll need 1 mole of oxygen molecules. I'll need 2 moles of water molecules. So it's basically keeping the same ratios, but we're going to count them in a bigger chunk that's much more convenient for us. One of the things that's going to be really important is that we need to be using what we call these molar coefficients, the coefficients inside the balanced reaction, instead of always doing things in grams. And the reason why is that grams is kind of like comparing apples and oranges. They're not really the same. Yes, they're both fruit, but they're not the same kind of fruit. If we convert everything into moles, it's like comparing apples and apples. Because not all molecules weigh the same amount, we can't use grams as a direct comparison. So we're always going to be trying to get to moles and use molar coefficients to do our problems. You will sometimes hear people say that mole ratios are the key to stoichiometry. The idea is that this mole ratio is the magical piece that allows us to do these conversions. And so we're going to have things like, if I have 3 moles of this, how many moles of that do I have? If I have 2 moles of this, how many moles of that can I make? If I don't give you moles to start with, you have to get to moles first. If I want to know how many grams, you're going to have to do moles first and then convert to grams. So this mole ratio is kind of the center. This is what we're trying to get to. Always get to moles. It's the key to stoichiometry. So let's try to write some mole ratios. If this is the equation we're using, the mole ratios are any combination of elements related to each other. So for example, 2 moles of hydrogen needs 1 mole of oxygen. So you can see here, I've made a ratio set up as a fraction. You should notice that these fractions kind of look like conversion factors, don't they? And conversion factors lets us do dimensional analysis, which is what we always like to do here in this class. So these mole ratios will be set up in fraction form. Here you can see 2 moles of hydrogen can make 2 moles of water, represented here by this mole ratio. There's one more unique combination we can make, which is moles of oxygen to moles of water. Now, some of you might be saying, but what about the other direction? What if I did oxygen on top and then hydrogen on the bottom? Or water on top and hydrogen on the bottom, etc.? And that's great to notice, because just like any conversion factor, you can flip these also. So you can flip all your mole ratios. I'm not going to make you write all 6 of these, right? If you just wrote the top row or you just wrote the bottom row, you're totally fine. I know that we can flip them. What I'll be looking for is that you have the unique combinations of elements together. Understanding that you can flip them is really important, because that's going to allow you to figure out which units need to be canceled for our dimensional analysis portion. So right now, I'd like you to write out all the mole ratios for this problem. Try to find all the unique combinations. You do not have to write them all flipped. I'll get you started. If you notice, what I tend to do when I do these problems is I like to start on the left and go to the right. So I'm going to start with C2H2 and relate it to oxygen. Then I'm going to do C2H2 to water. Then I'm going to do C2H2 to carbon dioxide. Then I'll move over. I'll do oxygen and water, oxygen and carbon dioxide. Then I'll do water and carbon dioxide. If you do it like that, kind of a left to right, you'll get all the combos and you won't double up on anything or miss anything. So the mole ratio of C2H2 to O2 is a 2 to 5 ratio. It does not matter if you put the 2 moles of C2H2 on top or bottom. It's the same mole ratio because we know we can flip it. Next, C2H2 to water is a 2 to 2 ratio. Now you're going to notice I did not simplify this. That's very important because these mole ratios should represent the equation as it's written. Your calculator will reduce this for you when you get to that part. But if you were to say 1 mole and 1 mole, that would not match the balanced equation that we're dealing with right now. So do not reduce your mole ratios. Leave them be. Fix them at the end in your calculator. Let the calculator do the work for you. Next is C2H2 to carbon dioxide, 2 to 4. And you can see one more time, I did not reduce this. I left it alone. Next we move on. Let's do oxygen and water. That's a 5 to 2 ratio. Next is oxygen to carbon dioxide, which is a 5 to 4 ratio. And last, water to carbon dioxide, which is a 2 to 4 ratio. If you wrote any of these flipped, totally fine. Not a big deal. They are the same thing. Okay, next, let's start taking these mole ratios and doing something with them. Just talking about what the mole ratios are is not super helpful. It's interesting to know how much you need, right? It's interesting to know what these ratios are, but it doesn't really do anything for us until we put them into a dimensional analysis problem. So we're going to use these mole ratios as conversion factors. So let's start with this question. How many moles of carbon dioxide can be made from 19.46 moles of oxygen gas? Just like a molar conversion, I start with my known value. I use my conversion factors to help get me to the final answer by canceling my units. So I start with 19.46 moles of oxygen. I want to get rid of moles of oxygen, so I'm going to need moles of oxygen on the bottom. And I'm wanting to know how much carbon dioxide that would be. So carbon dioxide will be on the top. So let's look at our balanced equation, and we see that there are 5 moles of oxygen for every 4 moles of carbon dioxide. That becomes my conversion factor. 5 moles of oxygen, 4 moles of carbon dioxide. The moles cancel. I'm left with moles of carbon dioxide as my answer. You're going to notice we can no longer just say 19.46 moles, because now we have to know moles of what? Moles of oxygen or moles of carbon dioxide. So your unit needs to include the formula from now on. That's very important. Okay. All right. Now, one thing to make sure you realize is you can go both directions here. You don't always have to start with a reactant. Maybe somebody told you how much product you made and they want to know how much you started with. So your starting and stopping places do not have to be on certain sides of the reaction arrow. It does not matter. So here, if you made 13.42 moles of water, how many moles of oxygen gas did you start with? Start with my known value. Now let's look up here. It's 5 moles of oxygen gas for every 2 moles of water. So because I want to cancel moles of water, the 2 is going to go on the bottom. And the 5 moles of oxygen will go on the top. Moles of water cancels. I'm left with moles of oxygen. And then I get my final answer. So sometimes we may not want our answer in moles. We often want grams or milligrams or something like that, or maybe we want molecules. So we may have to add on some extra molar conversions either at the beginning or at the end once we kind of have figured out that mole ratio portion. So what I like to use is something called the mole highway. And the mole highway is basically just a map that shows you what your allowed conversions are. If you remember when we did molar conversions, we learned there were only certain pathways you could take, grams to moles to molecules, right? This is just like that, but bigger, because now we have more things going on and we have some extra options. So let's look at the mole highway. So let's start on the left side. You're going to notice it says things like atoms of A, molecules of A, moles of A, grams of A. A is whatever you know, whatever your starting value is. I like to just label things with A's and B's because trying to write all the formulas every time gets really annoying, takes up a lot of space. So I'll label things A and B. On the right-hand side, it's whatever it is we're solving for. It's the new compound that we're looking for. Atoms of B, molecules B, moles of B, etc. And right smack in the middle, right in the halfway point, is our new special magical thing, the mole ratio, right? And if you notice, if you ever want to convert from one substance to a new substance, you can't get there unless you go through that mole ratio using your balanced equation. That's where these numbers come from, okay? So you can see along the arrows, I told you what the conversion factor is. For example, grams to moles is molar mass, which will be a certain number of grams over 1 mole. Molecules to moles is Avogadro's number. You can see here 6.02 times 10 to the 23rd particles per mole, just like we've always done. There's a couple extras added in here. Density sometimes pops up. It's nice to be able to go from a volume to a mass using density. We'll learn later in the year something called the ideal gas law, which allows us to use a little bit of algebra and some topics we haven't learned yet in the gas chapter to be able to go from a volume to moles. Molar volume, if you're at a certain temperature and pressure, called STP, standard temperature and pressure, you can use 22.4 liters per 1 mole as a conversion factor. It's a weird fact that every single gas takes up 22.4 liters when you have a mole of it at this special standard temp and pressure. So this looks overwhelming, but if you look at each individual arrow, these are all basically things you know how to do already. The only thing you don't know how to do is this ideal gas law part, which we'll deal with later. But you know how to go from molecules to moles. You know how to go from moles to grams. You know how to do all these things. All you have to do is now add in a mole ratio so that you can get to the other side. It's important to know that on the left side, your molar mass is going to be the one for the molecule A, and on the right-hand side, your molar mass is for molecule B. So make sure you're paying attention to which formula you're using during your conversion. There's so many routes, I don't know what pathway to use. Well, use your mole highway. Put a little mark or your finger on where you're starting, put one on where you're ending, and just trace the arrows and figure out where you need to go. And then over time, you'll get to the point where you'll do this so much, you'll kind of accidentally memorize that mole highway. But until you're at that point, go ahead and use it, right? Look at it, mark it up, put your fingers on it. And then at that point, once you know your pathway, you know the rest. Dimensional analysis, flip conversion factors, cancel your units, and that's it. Okay. All right, everybody. That was it for this lesson. I hope that was helpful. Bye.